Welcome to my video talk. It is difficult to give a video talk and because there is no audience. So in order to simulate audience, I got with me somebody, an invisible man sitting in this chair. The invisible man asked me a question. What am I working on? Well, I'm working on understanding power consumption in communication systems. What interests me is that power consumed in today's communication systems, you think of lossless systems or lossy systems, the encoding and decoding power or the processing power is actually a dominant component of the system power. This is what I'm most curious about because this really involves taking into account complexity of encoding and decoding in a very concrete, very tangible manner. Okay, the next question. Why do encoding and decoding consume any power? Well, encoding and decoding need to consume power because they are implemented in physical circuits. Why do circuits consume power? Circuits consume power because they are a bunch of computational nodes, basically gates, that are communicating to each other over wires on a chip, right, in a circuit. Now, essentially, a circuit, therefore, is a communication network. Any communication network needs power to run, and hence a circuit also needs power to run. Okay? Yeah, exactly. See, this already suggests a way to analyze circuits and understand the power consumed by circuits. Use tools from network information theory in order to understand circuits. Okay, what kind of results do I get? The kind of results that I get are as follows. The goal is to minimize not just, let's say, the transmission power or the storage power in case of lossless source coding, transmission power in case of channel coding, or measurement power in case of compressed sensing, but the goal is to minimize the total system power, where I'm taking not just these more commonly understood terms, but also the power required to encode and decode, right, which takes into account complexity. So it turns out that if you want to minimize this total power, you do not want to operate close to the fundamental limits on rate in information theory. In fact, you want to operate far from these fundamental limits if the error probability goes to zero. What's the intuition behind these results? The intuition is also simple. We know in information theory that we need long block lengths in order to approach capacity or drive error probability to zero. What these results show is that there is a finer thing that needs to happen. That on a chip, you need to have a lot of communication. You need to have a lot of mixing of information at the encoder and a lot of unmixing or demixing of information at the decoder in order to take advantage of these long block lengths. And that is why encoding and decoding circuits need power in a very fundamental manner. Okay, what are the kind of tools, you ask? The kind of tools that you need in order to derive these results, I use two tools. One of the tools is about understanding how much neighborhood size is needed at, let's say, the decoder in order to decode information about the particular message that it is interested in. So for each bit of the message, how much is the size of the neighborhood? Now this neighborhood size can be much smaller than the size of the entire block length, but it connects to computation in a very natural manner because by message passing on a chip, you can only reach out to a finite neighborhood size. That's the first tool, and that gives an understanding of how many clock cycles are required in order to compute, which really is about how much power is consumed in the nodes at the encoder and decoder. There is also wire power consumption, which can be significant, and an understanding of wires, which is really trying to understand communication links on a chip, is obtained by using cut-set bound style analysis on these on-chip networks. So that is all. Thank you, Chair, and thank you also the conference chairs for letting me do this video presentation, Suhas and Rudiger especially, and a special thanks also to Amin Gohari, who is going to present my poster in the next session. Enjoy the conference.